Hello everyone. This is the video for lecture 21 and today we're going to finish up chapter 22. In the last lecture we talked about reflection. So we were talking about incident lights reflecting off of a surface. The typical case actually is that you have an incident ray that hits a surface. Some of that light crosses into the surface and some of it reflects. The light that crosses into the surface, we say that it's refracted. And we say this because usually when the incident ray passes over into the glass, it bends from the straight line that it was traveling in. So the incident ray here, if it continued on in a straight direction, it would follow that dotted line. But as it passes into the glass, it actually bends a little bit from that path. So some of the incident light on the glass passes through the glass and it gets bent as it passes into the glass, and some of it is reflected. The reflected ray follows the law of reflection that we learned about last time, that theta 1 is equal to theta 1 prime. And the refracted ray is what we're going to learn about today. Before I continue, I want to mention the last bullet point that says you don't only have to go from air into glass, for instance. You can start at the bottom, at point B, and shine a laser up toward the air. And when the laser crosses from the glass into the air, it will also bend. In this case, you also have a reflected ray, but it's going to reflect off of the glass-air boundary back into the glass. The angle that the refracted ray bends also follows some rules. So first of all, let's mention that to measure the angle of refraction, you draw a normal line, and then you measure the angle between the normal line and the refracted ray. Now the angle of refraction, here called theta 2, depends on the speed of light in the two different media. In a vacuum, where there's nothing at all, light travels at the fastest speed in the universe, called the speed of light. When light passes from a vacuum into air, it actually slows down a little bit. When the light passes into glass, it slows down even more. In this example, let's say that air is the first medium and glass is the second medium. Then the speed that light travels in air we will call V1, and the speed light travels in glass we'll call V2. Then the refracted ray, or the angle of refraction, behaves according to this equality. We'll see a more common form of this equality in a few slides, but the general rules are that when light refracts into a material where it moves slower, it has to bend toward the normal. So when light passes from air, where it moves very fast, into glass, where it slows down, it has to bend toward that normal line. And then this works in reverse too. If light refracts from a material where it's going slow into a material where it moves fast, then it has to bend away from the normal. So if we start with the light at B and it's moving upward, it's moving through glass where it's relatively slow. It passes into air where it's moving very fast, and it has to bend away from that normal line. We'll characterize this behavior using something we call the index of refraction. For this we use the small letter n, and this determines the amount that the light ray actually bends. So n is equal to the speed of light in a vacuum divided by the speed of light in the media that you're looking at. So for air, for instance, it would be c divided by the speed of light in air. Now n is a speed divided by another speed, so it's a dimensionless number. It has no dimensions at all. C is a constant, 3 times 10 to the 8 meters per second, and this is just the speed of light in a vacuum. This also makes n a constant for a medium, similar to density, right? Every piece of gold has the same density. Similarly, every piece of glass has the same index of refraction. The caveat there being that there's actually several different types of glass, but if you narrow it down to one type of glass, they will all have the same index of refraction. The speed of light in a vacuum is the fastest speed that you can possibly go in the universe. So whenever you go into any other medium, you're always moving slower, or the light is always moving slower. This means that c is always greater than or equal to whatever the speed of light is in the medium. If I divide by v, I'll get c over v is greater than or equal to 1. And this means that n, the index of refraction, is always greater than or equal to 1. We're still talking about the ray model of light, but I want to do a quick aside and talk about light as a wave for a second. For waves, we know that velocity is equal to wavelength times frequency, and the frequency of a wave is determined by the source. So in the lab we did, the frequency of those standing waves was determined by the vibrator that it was attached to. We had set the vibrator to 120 hertz, and that was the same for all the waves. This is also true for light. So if you have a light bulb or some other source of light, it produces light at a certain frequency. And when that light passes from air into water into glass, the frequency of that light does not change. But the speed does change. So when the light passes into a medium where it has a slower speed, v decreases. The frequency stays the same, so this means lambda also has to decrease to compensate. So if the speed of light decreases in a medium, then the wavelength of that light also decreases. Snell's law is the law of refraction that acts as the counterpart to the law of reflection we learned last lecture. The law of reflection said that if you have an incident ray and a reflected ray, that theta 1 was equal to theta 1 prime. Snell's law is a little more complicated for the incident and the refracted rays. It says that n1, so the index of refraction in the first medium, times the sine of theta 1, the angle measured from the normal to the incident ray, is equal to the index of refraction in the second medium times the sine of the refracted angle. Snell's law is an equation for two different mediums, indicated by the 1 and the 2 in the subscripts. But often it's convenient to think of Snell's law as just relating to one medium, and we can do this with the equation n sine theta is equal to constant. You don't really have to know the reason why we can do this, but in case you're interested, it's because the left-hand side of this equation only depends on the first medium. In this example on the right, I have an incident ray passing through air, passing into a second medium, but the incident ray is passing through a material that has an index of refraction n1, and when that incident ray strikes the boundary between the two medium, the incident ray makes an angle of theta 1 with the normal. Okay, so I can, I have the example here where the incident ray refracts into glass and it makes a certain angle. But I can take that glass away and replace it with, say, water. Then the incident ray is going to approach the air-water boundary, and nothing changes about the incident ray. So n1 will still be the same, and theta 1 will still be the same. When the incident ray crosses into the water, it will refract at a different angle, but the upper half of this picture stays the same. So the left-hand side of this equation is unchanged. Said a different way, It doesn't matter what is happening on the right-hand side of this equation, the left-hand side is constant. Thus, n times sine theta is equal to a constant number. At the bottom, I have a link to a simulation where you can play with this reflection and refraction. At the top, you have a laser beam that's shining from whatever you choose the first medium to be into whatever you choose the second medium to be. So the laser shines onto the boundary between the two mediums. Then some of it is reflected, some of it's refracted, and you can just sort of see how the angle changes as you move the laser around. You can also change the index of refraction for each. So for instance, if I set the top and the bottom to be water, then the two materials are the same, so there's no reflection or refraction at all. In any case, it's there for you if you want to play around with it. In section 22.6, they explain Snell's law using Huygens' principle. Huygens was a Dutch man whose name I'm not pronouncing even close to correctly. But in any case, the idea behind Snell's law can be summarized with the following mechanical analog. You start by rolling a barrel on concrete, and you roll it toward grass at an angle. So while the barrel is on concrete, it's rolling relatively fast, and both ends are moving at the same speed. When the barrel passes onto the grass, the left end is going to roll more slowly because the barrel does not roll as fast on grass as it does on concrete. However, the right end of this barrel is still rolling relatively fast. So left end slow, right end fast means the barrel is going to rotate a little bit. When the barrel rotates onto the grass, it has deviated from the straight line trajectory that it was initially traveling. So the barrel has refracted. And this is something maybe you experienced when you were growing up if you roller skated. So you're skating along down the street, and maybe your right skate passes onto some grass. Right? So the right skate starts to move slower, while the left skate is still moving relatively fast. This causes you to rotate toward the grass. Let me point out that this is just a way to help you remember how light bends when it passes from one medium into another. But an actual explanation requires something like Huygens' principle, which I'm not going to go into, because it involves a lot of geometry, which I don't think you'll care to see. So here's a question. You have a laser beam that starts in the first medium on the right side of this figure. It crosses the boundary between the two mediums, and then it refracts into medium 2. So which of the following is true? I will give you the answer in one of our class meetings, but as a hint, let me remind you that you have to draw a normal line at the proper location, which is perpendicular to the boundary between the two mediums. And then you can compare the angle of refraction to the angle of incidence. This question is a little bit different. Rather than having a sharp boundary between medium 1 and medium 2, you have a material that has an index of refraction which gradually increases as you move down through the medium. So the question is, which of these pictures depicts the actual path that the light will travel? For this question, my hint is to think about what happens to light as it passes from a less optically dense material into a more optically dense material. The idea behind the last question can be used to explain desert mirages. So if you're not familiar, a mirage is, so you're stuck in the desert and it's very hot, and you look out in the distance and you see a shimmering pool of water. But when you walk over there, there's just sand, nothing at all. The reason this happens is because regions of air with different temperatures actually have different indices of refraction. So in the desert, when it's very hot, the ground is much hotter than the surrounding air. So the sand of the desert is very, very hot. And even though the air will feel hot, it's not as hot as the sand. You can experience this if you go to a beach on a hot summer day. The beach sand can be too hot to even walk on even, but the air is relatively cool. So light rays that pass close to the ground bend in a similar way to the light was bending in the previous question. The light that passes close to the ground can then bend upward and reach your eye, and it can make you think you see things that are not actually there. This is maybe better explained with the diagram at the bottom. So if you've ever driven in traffic on a hot day, you may have noticed that it looks like the car in front of you is driving over these puddles. It looks like the light from the car is reflecting off of these puddles and passing into your eye. So you see these puddles on the ground, but when you drive forward, those puddles aren't actually there. It's just dry road. So what's happening is you have sunlight bouncing off the back of this car, and it bounces off the car in all directions. Some of that light bounces toward the ground, but since the ground is hot and the air close to the ground is also hot, that light ray can bend upward and reach your eye in the car. So then when your eye sees this light coming towards you, what your brain is telling you is that that light came from a spot on the ground, somewhere in this region. Due to variations in air temperature and movement of the air, the light that's passing close to the ground can appear like it's shimmering. Okay, and this can make it look like there's a puddle of water on the ground. So then as a whole, what you're seeing is some of the light coming directly from the back of the car. That is, in this image, it's the actual car itself. And you have some light that appears to be coming from the ground behind the car. And that light appears to be reflecting off of a puddle. But that puddle's not actually there. Section 22.4 is on prisms. I'm going to skip it because 22.5 is similar, but the topic's a little more interesting. In summary, though, light is a combination of all colors. White light is a combination of all the colors of the rainbow. When light passes through a prism, the different colors have different indices of refraction, so they refract at different angles. This is why the light spreads out and you see all the different colors. And this is what happens with rainbows as well. Rainbows are caused by a combination of reflection and refraction. You have sunlight that comes in, it's white light that's a combination of all the colors. It enters the raindrop, and the different colors refract at different angles. Red light refracts the least, violet light refracts the most. When the light hits the back of the raindrop, some of that light is transmitted into the air behind the raindrop, but some of it's reflected inside the raindrop. Remember, light, when it crosses from one medium to another, you always have some reflection and some refraction. So in this case, you have some light that reflects inside the raindrop. That goes back toward the front of the raindrop, and then that light, as it crosses back over into the air, it refracts again. Okay, so then you also have the violet doing this. It reflects off the back, and then it refracts again into the air. The combined effect of this reflection and refraction is that the sunlight that comes from the left of this figure reflects back toward the left, and it's separated into the different colors of the rainbow. The middle picture shows this in full. You have the sun shining light from the left side. the light refracts off of raindrops on the right side. This separates it into the different colors, and those colors eventually reach your eye on the ground. So you're seeing the sunlight that's been separated into different colors. Now, the different angles of refraction of the light, all the different colors, this always causes red to be the top part of the rainbow, and the violet or the blue will be always on the bottom. You can see this in the picture of a rainbow on the right-hand side. Hopefully this looks very similar to all the rainbows you've seen. What's interesting about this picture, though, is the second rainbow that's sort of dimmer on the right-hand side. Oftentimes that second rainbow is too dim for you to actually see, but it's always there. And the reason for this is because of a second type of reflection happening inside of the raindrop. That first very bright rainbow happens because of light that enters near the top of the raindrop, and then it reflects and exits near the bottom of the raindrop. The secondary rainbow is due to light that enters near the bottom of the raindrop. This light reflects twice inside of the raindrop, and then it exits again from the front. Each time the light reflects inside of the raindrop, some of that light is lost because of transmission. In the first case, when the light reflects off the back of the raindrop, you have some light that passes out the backside. So when the light refracts toward the front, most of the light is reflected toward the front, but some of it actually passes out the back. In the second case, you have one reflection where some of the light is transmitted out the back, and then you have a second reflection where even more of the light is transmitted outside of the raindrop. So by the time that light reflects all the way back to the left, more of it is lost. So this is why the primary rainbow is due to one reflection, and it ends up being brighter than the secondary rainbow. Around sunrise and sunset, you may have noticed that the sky is typically more red or orange than it usually is. This is because blue and green and yellow light is scattered more than red light. So interestingly, if you form a rainbow with only this red light, you can get what's called a red rainbow, and that's shown in the picture on the right-hand side. Basically, the entire reason why I explain secondary rainbows to you is so I can show you one of the best videos on the internet. If you've never seen the double rainbow guy video, highly recommend that you check it out. I'll show you a teaser of it here, but you should really see it in full. It's a video of a man, he sees a double rainbow, and he gets rather emotional about it. In all sincerity, though, it is one of the most wholesome videos on the internet.
Double rainbow, oh my god. It's a double rainbow all the way. Whoa, that's so intense. Whoa, man. Wow. Whoa. 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 Oh my god, oh my god. Oh, oh my god. Woo. Oh my, wow. Woo. Yeah. Oh my, oh my, oh my god, look at that.
And it gets even better when he starts crying halfway through. Let me point out that he claims to be sober during the filming of that video. An interesting phenomenon can occur when light starts in a slower medium and passes into a faster medium. Let's start by thinking about the barrel. Imagine the barrel starts rolling on the grass, and it's rolling toward the concrete, but it's almost parallel to the boundary between the grass and the concrete. As that barrel approaches the concrete, the left end of the barrel is going to start to roll on the concrete, and the left end is going to roll faster than the right end. This is going to cause the barrel to turn and start rolling alongside the boundary. So the barrel that should have been transmitted from the grass onto the concrete instead just rolls parallel to the boundary. It doesn't actually transmit onto the concrete. This also happens with light. It's called total internal reflection. There are two requirements for this to occur with light. The first is that light has to start in a slower medium and transmit into a faster medium. And the second is that the angle of incidence must be large enough. So in this case, the angle of incidence would be the angle between the vertical and the direction of the barrel. So this angle right here has to be large enough for it to occur. And then I do want to note that this effect that you will see, it can happen on the boundary of any two surfaces that meet these conditions. The boundary doesn't have to be a reflective boundary. We can see this in the simulation. We start off with a laser beam inside of water, because water is relatively slow for the speed of light, and it has to pass into air, which is relatively fast. The angle of incidence is this angle right here, and when the angle of incidence is small, you get the picture that you expect. Light crosses over the boundary, it refracts. In this case, it refracts away from the normal, and some of the light reflects. Now, if I increase the angle of incidence, at some point, you will see that that refracted light disappears entirely. Essentially, it travels parallel to the boundary, and at that point, the light is just totally reflected inside of the water surface. Now, if I'm calling the angle of incidence theta 1 and the angle of refraction theta 2, then the total internal reflection occurs when theta 2 gets to be 90 degrees. When this angle down here is 90 degrees. Once that angle is 90 degrees, theta 1 becomes what we call the critical angle. Using Snell's law, I would write N1 times the sine of the angle of incidence, which I'm now going to call the critical angle, equals N2 times the sine of 90 degrees. So the refracted angle is 90 degrees. The sine of 90 degrees is just 1, so I can ignore that. And I can solve for sine theta with this equation at the bottom. I will get sine theta c is equal to N2 over N1. This is how we can determine the critical angle between two different media. Then, any angle of incidence which is larger than the critical angle will produce total internal reflection. And this we can see in the simulation as well. Once I pass the critical angle, where I get total internal reflection, any angle of incidence greater than that critical angle will give me total internal reflection. And a technical side note, the left side of this equation, sine of theta, is at most 1. Sine in general has a maximum at 1. So the sine of theta will always be less than or equal to 1. If the left-hand side of the equation is less than or equal to 1, the right-hand side of this equation also has to be less than or equal to 1, since they're equal to each other. If I rearrange this, I get N2 less than or equal to N1, and then I can actually drop the equality, because you do not get total internal reflection if the two mediums have the same index of refraction. So this tells me that in order for total internal reflection to occur, I need N2 less than N1. This means that N1 is a slower medium than N2. So medium 1 is more optically dense, and this matches up with the observation we had on the previous slide, that light has to start in the slower medium. And this is why in the simulation, if I start with light in a faster medium like air, and it travels into a slower medium like water, I will never get total internal reflection. I will always have this refracted ray at the bottom, no matter where I move this angle of incidence. Total internal reflection is a cool and actually very useful phenomenon from physics. So if you have the proper materials, you can actually cause light to bend along curves. This is shown on the right. You have a plastic tube that's bent, and the light travels into the tube. It's total internally reflected throughout the tube so that it exits the tube at a different angle. Right? It has changed its direction. This is the idea behind fiber optics, which you might have heard of. You bundle together a bunch of thin tubes. The tubes are flexible, so you can bend the tubes, and light travels along the tube, so you can bend the path that light is traveling. Then you can bundle these fibers together into these long cables, and you can send light signals down these cables, and the effect will be very similar to what happens when we send electricity through wires. But there are advantages to using fiber optics. For instance, fiber can carry larger volumes of traffic. The data can be sent faster. So the internet that you're probably using is sent through an electrical wire currently. But they're rewiring large parts of this country to use fiber for their internet instead. Here's a video that demonstrates the effect. On the left side, you have set up a laser that shines through this tube of water, and if there was no water pouring out the right side, that laser would just continue on in a straight path and end up somewhere over here. But instead, there's a hole in this tube, and water is pouring out the side of the tube. Now, light travels slower in water, so when the laser tries to leave the tube, it reflects, total internally reflects off the top of the water. It reflects down to the bottom, back up to the top, down to the bottom, etc., etc. And you can see the light ray actually travels all the way down to the bottom here. As the video goes on, you'll see the stream get weaker and weaker. So the light will bend more and more until it gets to a point where the water bends too much and the light can no longer total internally reflect, and the light instead will just pass to the right, and there will be no light being transmitted by the water. I'm going to leave you with two examples for you to do today. The first is example 22.2 in the book. In this example, you have an incident ray in air that travels into a pane of glass, refracts, and then it travels out of the glass and refracts again. I do want you to work through this on your own, but I want to explain one thing to you. At some point, you're going to have to solve an equation that looks like this. You'll have sine of theta is equal to 0.329. In order to solve this, you have to use the inverse sine function on your calculator. In equations, I would write theta is equal to sine to the power of minus 1 of 0.329. This to the power of minus 1 it's not the same as with a number. If I take 10 to the power of minus 1, for example, this means I do 1 divided by 10. But with the sign, it means inverse function. So you have to find the special button on your calculator that is sine to the power of minus 1. So again, let me reiterate. Sine to the power of minus 1, or the inverse sine, of 0.329 is not equal to 1 over the sine of 0.329. And then one more thing, sometimes the inverse sine, or sine to the power of minus 1, is called the arcsine. So your calculator has one of these two buttons. The second example is 22.6, and this is an interesting application of total internal reflection. The idea is that if you're a fish and you're living underwater, all the light you see from above is refracted because it passes from air into water. But if the fish instead were to look at a more shallow angle, then the light that the fish sees will not come from the sky above, but it will have been total internally reflected from somewhere below. So if the fish is sort of skimming on the surface, the fish, instead of seeing the sky above, it'll see some reflection from the ground at the bottom. And this will occur when the angle is larger than the critical angle. And that's all I have for you today. This finishes up chapter 22. Next time we'll start chapter 23 on mirrors and lenses. Have a good one.